Okay, hello, SmartThinks people. It's nice to meet you online, and I'm Benyi Cao. The title of my topic today is Superabsorbent polymer-based self-immune and self-healing soil cement systems. So first, we need to know what soil cement systems are. So soil cement systems are widely used in geotechnical and geoenvironmental engineering. So basically, when we are encountered with difficult, problematic, or weak soils, we want to improve the ground so that the soil can have the engineering properties we're looking for. And then we can construct the infrastructure either in the soil or on the soil. So here are some examples of the soil cement systems we use in civil engineering. The first one is subgrade stabilization, and then we have solidification stabilization of industrial contaminants, and we have ground improvement for the foundation of a building, and of course, we have cut-off wall constructions. So my PhD work is basically focused on the last application, which is cut-off wall constructions. But today I will cover both cut-off wall construction and also subgrade stabilization, which is a work of a former colleague whose name is Jintao Chen. So first, let's have some look at the background of the two types of widely used soil cement cut-off walls in the UK. The first one is cement bentonite slurry trench cut-off wall. So this is a one-phase constructed cut-off wall. Basically, you first mix 5% bentonite, 20% cement or cement substitute like GGBS or fly ash together with 75% water, and you hydrate the water for maybe 24 hours, and then you have a homogeneous cement bentonite slurry. And then you dig a trench around the contaminated site you want to keep contained. And then you pour the cement bentonite slurry into the trench, and maybe after a few days or weeks, the cement bentonite slurry can self-harden, and you got a in-ground barrier. So the advantages of this kind of cut-off wall is first, the slurry quality can be very well controlled because you mix the slurry on site, and then you just need minimum space that is required for the machinery and the construction. And then this design is independent of the site geology because you just need to dig a trench. You don't use the in situ soil. In addition to soil cement slurry trench cut-off walls, we have another technique used for the construction of cut-off wall, which is soil mixing technology. So soil mixing technology was first used for ground improvement, and then like 30 years ago, this technology has been adopted for the construction of cut-off wall. So basically, we use an auger and we mix a grout. The grout consists of 50% cement and GGBS and 50% water. You just inject this grout through the auger into the in situ soil, and you have the blade at the tip of the auger, and you rotate the blade so the injected grout can be mixed with the in situ soil, and then you have the overlapped auger mixed grout soil columns. The advantage of this kind of construction technology is it has reduced spoil and disposal, and it has reduced the risk for workers, and also the depth of this cut-off wall can be achieved like basically 20 or 30 meters below the surface, below the ground. And also compared to the cement bentonite slurry trench wall, the soil mixing technology will have high strength because you mix the in situ soil, which can act as a kind of aggregate. So despite the intensive use of these soil cement cut-off walls and also soil cement subgrade for pavement or highway, these kind of soil cement systems can be damaged that caused by mechanical, chemical, and also environmental stresses. So let's have a look at the damages that can be caused, that potentially can be caused. First, in many northern parts of the world, we have freezing-thaw cycling problems because in winter the water can be frozen, and the freezing process can produce volumetric expansion that can cause the crack. And also we have cracking due to the desiccation above water table. And around the water table, we also have the cracking problem that's due to the wet-dry cycling caused by the changing water table height. And in addition to these environmental stresses, we'll also have chemical attack in some polluted sites. For example, the crack can be caused by acid attack, can be caused by sulfate attack, and also some heavy metal and organic contaminants can make the soil and cementitious matrix have a weak structure, which is also bad for the serviceability of the cutoff wall. So my work is basically introduce self-immune and self-healing concept to geotechnical engineering materials, because in previous lectures you had in this training school, you will find that most of these smart and resilient materials is just focused on structural materials such as cement paste, mortar, and concrete materials. So to date, very little attention has been paid to the incorporation of such resilient materials concept into geotechnical and geoenvironmental engineering. But we need to note that the self-immune and self-healing is extremely attractive to geotechnical engineering. I would say maybe more important than the structural materials, because many of these geotechnical infrastructures are buried underground, which means the damage cannot be detected. And if the damage happens, it's extremely difficult to repair and also maintain the infrastructure. So the self-immune and self-healing approach I'm presenting today is superabsorbent polymer, which is also called SAPs. So SAPs are kind of copolymer of acrylamide and acrylate. So it has a particle size of like 100 microns. So you can see from the left figure, the SAP can absorb a large amount of water, and then this absorption process is reversible. So when water evaporates, the SAP can shrink. So in the right figure, you can see the SAP we used is supplied by BASF. It's a German chemistry company. And in deionized water, this SAP can absorb up to 360 times water of its own weight. But when in other solutions, the absorption capacity can decrease significantly, but also it's pretty well. For example, in cement bentonite slurry, the SAP can still absorb like 35 times the water of its own weight. So before we add SAP in soil cement system to achieve self-immune and self-healing performance, we first need to figure out the addition of SAP if it has an adverse effect on the engineering properties of the cementitious grout. If so, it won't be doable to add these SAPs in the soil cement system. So we first test the rheology of the cementitious grout. So you can see when we add up to 1% of the SAPs in the cement bentonite slurry, it has like three times the plastic viscosity compared to the control sample. But in reality, the recommended maximum plastic viscosity for cement bentonite slurry is 80 MPa/second. So even if we add 1% of SAPs in the grout, it is still below the maximum recommended value, which means the addition of SAP is doable, the grout is pumpable, and the workability won't be affected too much. And then we also look at the cement hydration process. Why we're looking at this? Because we want the cement, the set time of the cement be predictable. We don't want because when we add SAP in the soil cement system, it will slightly alter the water to cement ratio. So we don't want the cement hydration process become unpredictable. And from the curves, we can see that compared to the control sample, when we add up to 1% of SAPs, the cement hydration wasn't really affected, which is a good thing. And also we examined the effects of SAPs on the hardened properties of cement bentonite, which basically the strength and the stress-strain relationship. So for the strength, we can see that because the addition of SAP can slightly decrease the water to cement ratio, which means which means it can increase the UCS values. And also a more important thing is that the strain at failure become much larger, which is a good thing because that indicates the cement bentonite slurry cutoff wall can deform to a greater extent without cracking. That's the properties that we are looking for. So in terms of the self-immune performance, we add the SAPs into the soil cement system and we make the samples undergo dozens of the freeze-thaw cycles. And after that these 4 pictures shows the soil cement samples after 10 freeze-thaw cycles. From left to right, the SAP content increases. So you can see from these 4 pictures, fewer cracks can be identified with the increased SAP dosage. And the last figure shows when 2% of SAP is added into the soil cement system. So no cracks were observed on the 2% SAP sample, while various cracks and spalling can be observed on the control sample, which is a direct visual evidence of the improved self-immune ability of the soil cement after the addition of SAPs. And then we examine the porosity and the permeability of these SAP-containing samples. So from the porosity, we can see the increase in porosity after freeze-thaw cycles was significantly reduced by SAP addition. You can see the black line in the left figure is the control sample. After 10 cycles of freeze-thaw, the porosity increased significantly. And the green line is when 2% of SAP is added into the system and the porosity basically remained stable. So which means the 2% SAP was completely self-immune in terms of the porosity. And also we test the permeability of the samples. And it shows that after a total of 20 freeze-thaw cycles, the increase in the permeability of the 2% SAP sample was negligible, which means it's completely immune against the freeze-thaw cycles. So we proposed a mechanism of the self-immune system under the freeze-thaw cycles. So you can see from the 4 figures, first the SAP was added in the soil cement system and SAP was saturated during the mixing of soil cement. And with the cement hydration happens, the water is gradually released from the SAP to the surrounding cementitious matrix to help the cement hydration process. And this process can produce a protective pore in the matrix. And then water enters the protective pore during freezing. And then the water is frozen in the protective pores because this freezing process is happening in the pores instead of in the cementitious matrix, which means the volumetric expansion won't adversely affect the cementitious matrix and therefore avoiding the induced stress and also the cracking. So the basically the release of the absorbed water creates small cavities inside the soil, makes the soil cement matrix, and the cavities can serve as expansion vessel for water to enter and expand during freezing, and therefore develop a self-immune system against freeze-thaw deterioration. In addition to freeze-thaw, we also tested the self-immune performance of soil cement incorporating SAP under wet-dry cycles. And from this figure, you can say after 7 wet-dry cycles, when we add 0.6% and 1% of SAP in cement bentonite, it basically shows just one crack. And in contrast, when we look at the control sample, it's basically crumbled, and you can see various cracks on the surface of the sample. So we also test the permeability of these samples, and after 2 wet-dry cycles, you can see for the 1% SAP samples, the permeability just slightly increased, but for the control sample without any SAP addition, the permeability basically increased by an order of magnitude. So why the addition of SAP can help the soil cement system to develop a self-immune ability? We propose the mechanism is basically twofold. The reinforcement and the suction reduction due to SAP addition are believed to contribute to the improvement of crack resistance of the cement bentonite mixes. So the SAPs can reduce the matrix suction in 2 ways. The first, it can lead to the reduction of the contact between the free pore water and the cement particles. And second, it can increase the pore size in the matrix and thus decreasing the matrix suction. This is the knowledge of unsaturated soil mechanics. If you're interested, you can look into that more depth. So we also did the micro CT scan of these 2 samples. It's obviously that the control sample after drying, there are so many cracks, the sample almost crumbling, it is crumbling, and the SAP containing sample is like complete intact. So we extracted the 3D network formed by the SAP. On the right figure, the blue layer are the SAPs. So you can see the SAP film can act as a reinforcement in the cementitious matrix, and also the micropores are produced because of the release of the absorbed water of the SAPs. So these 2 things are contributing to the self-immune against the wet-dry cycles. And we also did the SEM analysis, and we can see here that the cementitious particles are basically wrapped by SAP polymer films, and that's basically act as a bridge between different cementitious particles. And we also observed a very great bonding between the SAP polymers and the cementitious matrix. And also, in addition to the self-immune ability we observed, we also investigated the self-healing performance. So this is the permeability. The yellow column is the initial permeability of the soil cement system after 28-day curing. And then we cracked the samples on the UCS frame. And after 20 days, we did the permeability test again to see if the permeability has been recovered. For the control sample without any SAP addition, the permeability, the damaged permeability after 20 days of healing period basically increased by 1 order of magnitude. And for the SAP containing samples, the permeability value still remains within the same order of magnitude as the undamaged permeability. So the self-healing mechanism proposed here upon cracking is that the sap is first embedded in the cementitious matrix, and there is a crack, and a groundwater ingressed into the crack, and the sap swelling behavior is triggered by the water ingress. Therefore, the sap absorbs a lot of water and also swells. So the swollen sap particles can seal and heal the cracks. So that's the mechanism. To validate the proposed mechanism, we also did a CT scan, and here we can see the blue things, the blue blocks, they are saps. So they occupied, and so we can see that the pores and voids in the cementitious matrix are fully occupied and blocked by the saturated saps. So in the end, some sap takeaway. I know it's almost lunchtime in the UK, so I have some takeaway for you. I hope you can keep in mind after this 20-minute talk. The first thing is that the addition of sap can improve the self-immune against the freeze-thaw. Why? Because sap produces cavities, and these cavities can serve as expansion vessels in the soil cement system. And the second thing is the self-immune performance against the wet dry cycles. And that's because sap reinforces the soil cement system, and also the sap can reduce the matrix suction. And the third thing is that the self-healing performance is increased by the addition of saps upon cracking, because sap can absorb water and swells. So the swollen sap can block the voids and the cracks. So the addition of sap into the soil cement system is like kill 3 birds with 1 stone. Okay, that's all. Thank you very much.
Thanks, Benyi, for your presentation. Does anyone have any questions?
Sorry, I can't hear any voice.
Maybe Claudia can ask if there's. You can just ask the question again.
Can you hear us now, Benyi?
Yeah, I can hear you.
So the question is, how did you segment the swollen SAP in the CT tomography?
Okay, so all the segmentation in micro CT scan is based on the density of different parts. So in this sap-containing cement bentonite system, we basically have 3 faces with 3 different densities. The lightest density is, of course, the voids and the cracks. So that's the density of air. And then we have a medium density of swollen sap that is basically similar to the density of water. And we have the heaviest phase, which is cement bentonite, which is a cementitious matrix. And based on the difference in the densities, we can tell apart these 3 phases, and then to extract a certain phase that you would like to investigate.
Okay. Actually, Claudia.
Okay, there is I saw there is a follow-up question. Sorry. I have found that after cement hardening, the saps have lost the swelling capacity, and therefore when you resaturate the sample, the saps are not fully swollen. Yes and no. the swelling capacity of SAP has not been lost because the adsorption and the deadsorption process is completely reversible, and so therefore the SAP, even if it has released the water during the cement hydration process, after encountered with the ingress water from the groundwater, the SAP can still swell again to the fully capacity. And therefore, I would say the SAPs are fully saturated and the swelling capacity is not affected. And
maybe Christos, can you give Claudia co-hosting rights so she can unmute herself? Because I'm feeling that she's frantically trying to type to keep up.
okay.
Can you hear me?
Yeah.
Thank you. First of all, sorry, I did not. First, I enjoyed a lot your presentation. Very nice study. I was saying that, of course, this reduction on the swelling capacity of the SAPs is reversible. But I have seen in many studies, and I myself have observed, it requires several cycles to, let's say, because when you put the SAPs in the cement slurry, the SAPs will also absorb calcium cations, for example. And if you, for example, resaturate the sample with pure water, the absorption of also calcium cations will happen, but this requires a lot of cycles. I don't know exactly on cement bentonite slurry. I was talking mainly from the experience of cement paste, but I have observed that the reduction of the swelling capacity is quite considerable after the first resaturation.
Yeah, thank you. That's a very good question. The first thing is that the cement bentonite slurry is slightly different from the cement paste solution because we use less cement content. Therefore, the calcium concentration in cement bentonite slurry is lower than in cement paste solutions. And yes, the thing you were saying is right. The calcium ions can affect the microstructure of the SAP polymers. Therefore, some of this swelling capacity can be affected. But that's after many cycles. And here for self-healing, I think we are just looking for a few of these cycles of damage and self-healing. We're not really looking at the like 100 times of the cycles, but we haven't tested the like how many times the SAP can, after how many times of this adsorption and deadsorption cycles, the SAP will lose its swelling capacity completely or significantly. I think that's for the future work and it's worth investigating. Yeah.
Thank you.
Thank you.